In this video, we will review the trigonometry facts that you need to know for physics. Now, this is crucial information for your success in physics, but professors and textbooks often assume that students remember this information from high school, and therefore your textbook or your professor might not spend very much time on this material. But that's not because it's not important, it's because they kind of think it should be easy because you saw it in high school. But my experience is that a lot of students might not have really ever learned this material very clearly in high school, and even if they did, they forgot it pretty quickly. So I think most students need a slow, careful review of this crucial information for their physics class, and that's what we're going to do in this series of videos to cover this material. Well, let's start with an easy idea. What is the definition of a triangle? That should be pretty easy. So you should know a triangle is a figure with three sides. That's what the prefix tri means. Tri means three. So obviously, what's the name of this figure? Well, this is an example of a triangle. So why don't you try this exercise? See if you can figure out theta. Well, the idea you have to use here is that you should know that the angles in a triangle add up to 180. So we could do 80 degrees. Well, let's start by focusing on what's the question asking us for. The question is asking us for theta. It's always good to write down a symbol for what the question is asking us. And then we know that 80, I'll say 80 degrees, plus 70 degrees, plus theta, that should equal 180 degrees. The angles in a triangle add up to 180. So this would give us 150 degrees plus theta equals 180. So we can subtract 150 from both sides, and we get theta is 180 minus 150, or 30 degrees. Whenever you get an answer, it's good to put your answer into your sketch. So I'll build that answer into the sketch. Actually, we probably should have started by building the question into the sketch. So we should make a note to ourselves that this is what the question is asking us for. And now we've figured out that that is 30 degrees. Okay, so that's some simple math that involves a triangle. So what's the idea that we used there? The angles in the triangle add up to 180. That's an idea you should already have known, but that's something you need to keep in mind throughout your physics course. There's a fair amount of geometry that comes up in physics, and sometimes in order to figure out what we need to keep in mind that the angles in a triangle add up to 180. All right, so in this video, we're going to be focusing on right triangles. Do you know what is a right triangle? By the way, I'm going to ask you a lot of questions in this video, and whenever I ask a question, I hope you will pause the video and come up with an answer. So what's a right triangle? A right triangle is a triangle in which one of the angles is 90 degrees. Do you know why it's called a right triangle? It's called that because a 90-degree angle is a right angle. So you could say a right triangle is a triangle that has a right angle. So for example, can you draw a right triangle? This would be a right triangle. You should know that we use this little box to indicate the right angle, the 90-degree angle. So this would be an example of a right triangle. Now, I hope you know that a triangle has three sides. So a right triangle is a type of triangle in general. Now, one of the important terms for right triangles is hypotenuse. Do you know what the definition of the hypotenuse is? Again, each time I ask a question, I hope you'll actually come up with an answer. You will learn a lot more if you're participating actively in the video. What's a hypotenuse? The hypotenuse is the side opposite the 90-degree angle. And then the other two sides are called the legs. So can you find the hypotenuse here? This is the hypotenuse because it's opposite the 90-degree angle. And what do we call this side? It's called a leg. And what do we call this side? It's also called a leg. So notice that the triangle has three sides. This is a side, this is a side, and this is a side. One of the sides in a right triangle is called the hypotenuse, and the other two sides are called the legs. How do you know which is which? The hypotenuse is the side that's opposite the 90-degree angle. That's very important. It's a very important skill to be able to find the hypotenuse. Okay, so can you label the hypotenuse and the legs of this triangle? It should be pretty easy. Remember, the hypotenuse is the side that's opposite the right angle, and here's the right angle. So this side is the hypotenuse, and then the other two sides must be the legs. That should have been pretty easy, but that should remind you, most students are probably used to seeing right triangles that look like this, where the legs are horizontal and vertical, and the hypotenuse is at an angle. But remember, the hypotenuse does not have to be at a diagonal, and the legs don't have to be horizontal and vertical. In your physics course, you will also see cases where the hypotenuse is in some other direction, or the hypotenuse could be horizontal or vertical, and the legs could be diagonal. It's even possible that they could all be diagonal. So the way you tell the hypotenuse is not by focusing on the horizontal and the vertical. The hypotenuse is the side that's opposite to the 90-degree angle. So how about in this triangle, which side is the hypotenuse and which are the legs? Where's the hypotenuse and where's the legs? I hope you thought about that. That was a trick question. That's a trick question. Remember, because the terms hypotenuse and legs only apply to right triangles, and this is not a right triangle because none of the angles is 90 degrees. Remember, the hypotenuse is the side opposite the 90-degree angle, but none of these angles is 90. So this triangle has no hypotenuse and no legs. It just has three sides. So remember, the hypotenuse is one of the sides of a right triangle. Most triangles are not right triangles, so they don't have hypotenuses. Pause the video and try this problem. There's a couple ways to do this. The one I want to focus on is we know that all the angles here add up to 180. But doesn't that mean that these two angles add up to 90, right? Because this is already 90. If this is already 90 degrees, there's 90 degrees left for the other two angles. So these two have to add up to 90. So we can say that 35 degrees plus theta equals 90. I guess we should have started by labeling the question. So the question here is theta. So we can use this equation. I think that's a little bit simpler than saying 35 plus theta plus 90 equals 180. Those come out to be the same thing, but this gives us easier calculations. I hope you can see these two equations would give us the same answer. So now we have to subtract 35 from both sides. Now what's 90 minus 35? That's 55 degrees. 90 minus 35 is 55 degrees, and we can build that answer into our sketch. 55 degrees, and you could check that 35 plus 55 plus 90 really is 180. This is something you'll have to do quite a bit in the class. So this is the 90-degree angle. We could call these two angles the acute angles to distinguish them from the 90. Maybe you know that acute means less than 90. So these are the acute angles because they are less than 90. So the idea that we used there was that in a right triangle, the two acute angles add up to 90. So you don't have to add up in a right triangle. You don't have to add up everything to 180. Instead, you can just take the two smaller angles and add them up to 90, and that makes the calculations a little bit easier. Okay, so there's our answer to that question. Try this problem. So here the question is asking us for alpha. We should build that into our sketch. And we use the idea that since this is a right triangle, alpha plus theta should equal 90. Now I need to solve for alpha, so I'll subtract theta from both sides. So if we subtract theta from both sides, we get that alpha equals 90 minus theta. So we know that this angle is 90 minus theta. So oftentimes in physics, you'll see what we could call a no number problem, a problem that doesn't give you any specific numbers. And you need to know how to handle that as well. So that's what this was. This was an example of a no number problem. Since there's no numbers, we can't figure out a number for alpha, but we can still figure out a mathematical expression for alpha in terms of the other variable. And that's an important skill for physics. So this would be our answer, 90 minus theta. I guess we could make that more specific here and put in the units. All right, so again, the idea we've used here is that in a right triangle, the two acute angles add up to 90 degrees. Now we know that a right triangle has two legs and a hypotenuse. Now, which of those will be the longest side? Can any of those be the longest, or is there always one of those that's the longest? What's the longest side of a right triangle? Well, did you know that the hypotenuse is always the longest side? And that's another idea that's often useful in, or sometimes useful in physics. You should know the hypotenuse is always the longest side of a right triangle. Does that match what we've seen in our previous examples? So you can see this is the hypotenuse, and I think you can see just from looking at it that this looks like it's longer than the two legs. By the way, the reason for that is because in a triangle, the bigger the angle that you're opposite to, the bigger the side. Well, in a right triangle, this is the biggest angle. The 90-degree angle is always the biggest angle of a right triangle. So the hypotenuse is always opposite the biggest angle. So since the hypotenuse is opposite the bigger angle, it's always the bigger side. I think you can see again here that the hypotenuse is the biggest side, bigger than the two legs. And the reason for that is because it's opposite the bigger angle. Okay, so you should just keep in mind what's the biggest side of a right triangle. The longest side of a right triangle is always the hypotenuse. That's another fact that's useful. Try this problem. Okay, it's always good to build the question into the picture, and the question is asking us for the length of this side. And a good way to figure something out in math is to use a variable to represent what you're trying to figure out. So I'll make up the variable q for the length of this side. And then do you know how to solve this? We haven't talked about this together because this is something you should really already know, the Pythagorean theorem. The Pythagorean theorem, if you know two of the sides of a right triangle, the Pythagorean theorem tells you how to find the last side. You know what the Pythagorean theorem says? Here's the Pythagorean theorem. So our hypotenuse here would be q. How do I know that's the hypotenuse? Because it's opposite the 90 degrees. That equals the length of one leg plus the length of the other leg. And you have to remember to square both of those terms. Okay, we could do this step by step, but instead I'll just do this in one step. I guess I'll break it into a couple different steps. So q squared here, that's 25 plus 81. That gives us 106. And then we need to take the square root of both sides. Now you should keep in mind that every number has two square roots. For example, one of the square roots of 9 is 3, and the other one is -3. Well, which square root do we want to take here? Well, lengths are always positive, so I want to take the positive square root of 106. The radical sign by itself means the positive square root. So that's what the calculator will take here. Square root of 106. So that gives us 10 point. I'll round that off to 10.30. It's always good once you've figured out an answer to build that into your sketch. So we know now that this length is 10.30. We could also have done this all in one step on the calculator. Square root of 5 squared plus 9 squared. And these parentheses tell the calculator that the whole thing is 1 square root, and that would give us the same answer. Okay, hopefully that's a review for you, but you should just keep in mind that the Pythagorean theorem is one of the tools that you might have to use sometimes. You will have to use sometimes in your physics class. Notice that you cannot use the Pythagorean theorem unless you can tell the difference between a hypotenuse and a leg. So remember, are the legs the horizontal and the vertical sides? Not necessarily. The hypotenuse could be vertical or horizontal. The hypotenuse is the side that's opposite the 90-degree angle. By the way, which of these sides would we have predicted would be the longest? Well, we would predict that the hypotenuse is the longest, and that turned out to be the case. That's a way you can use to check your answer here. If this answer had come out to be smaller than 9, that would indicate that we'd made a mistake, because the hypotenuse should be the longest side. So you should make sure that you memorize the Pythagorean theorem. Notice the Pythagorean theorem only applies to right triangles, because only right triangles have a hypotenuse. Try this problem. We should build the question into the picture, and we can make up a symbol for this unknown side. I'll call it L. And this is a right triangle, so we can use the Pythagorean theorem, which says that the hypotenuse squared equals the length of one leg squared times the length of the other leg squared. Our hypotenuse here is symbolized by D. One leg is Q, and the last leg is L. Don't forget to square everything. Now we want to solve for L, so we need to move the Q to the left. So I'll subtract Q squared from both sides. That gives me D squared minus Q squared equals L squared. And then we can take the square root of both sides. We want the positive square root because L is supposed to be a length. So we'll write that like this. We don't actually have to keep the plus sign here because this symbol by itself means the positive square root. This means the positive square root. I just put the plus sign here to emphasize that. Actually, maybe that's confusing, so I'll leave this plus sign out. This symbol means the positive square root. So if we want the positive square root, we can just write the radical symbol by itself. All right, and now I think we have our answer. We might also want to build that into your sketch if necessary, if you needed to use that answer in another part of the problem. Okay, so this is another use of the Pythagorean theorem. Here we used it on a no number problem. It's important to get used to using every technique that you might need in physics when you're doing just symbolic problems with no numbers. So we solved for L in terms of D and Q, which were the givens on this problem. So when can you use the Pythagorean theorem? When can you use the Pythagorean theorem? Anytime you know 2 of the sides of a right triangle. If you know 2 of the sides of a right triangle, then you can use the Pythagorean theorem to find the third one. And if you're given a symbol for something, then the rules are that we pretend that we know it. So even though we only know symbols for these 2 sides, we're allowed to pretend that we actually know their values. So we can use those 2 symbols to figure out the third side. Pause the video and try this problem. Well, did you see this is a trick question? I was trying to trick you into using the Pythagorean theorem, but the Pythagorean theorem doesn't apply here because this does not, we don't know that it's a right triangle. We don't know that it's a right triangle. It doesn't really look like one. Remember, you can only use the Pythagorean theorem for a right triangle. So what's the answer here? The answer is unknown. It's not possible to figure out. It's not possible to figure out the answer here. Remember, the Pythagorean theorem only applies to a right triangle because it involves the hypotenuse, and only a right triangle has a hypotenuse, a side that's opposite the 90-degree angle. Pause the video and try this problem. Okay, now we can go through this together. All right, so now we're starting to deal with the main purpose of this video, which is sine, cosine, and tangent. Now, you've probably already seen in your previous courses that there's a memory aid to help you remember what sine, cosine, and tangent stand for. And the memory aid is SOH CAH TOA. SOH CAH TOA. Here, O stands for opposite, H stands for hypotenuse, and A stands for adjacent. So the first thing we have to do is label the opposite, adjacent, and hypotenuse sides in this triangle. Well, it's easy to label the hypotenuse. The side opposite the 90 degrees is the hypotenuse. Now, who's opposite and who's adjacent? That's a little bit subtle. A lot of students don't understand this. Who is opposite and who's adjacent depends on which angle you're focusing on. So I'm going to start by doing part A. And in part A, we're focusing on angle theta. So I'm going to put an asterisk here to remind myself that we're focusing on angle theta for part A. So which of the legs is adjacent to theta? Well, that's Q. So this is the adjacent side. And which of the legs is opposite to theta? Well, that's V. So this is the opposite leg. So notice that opposite and adjacent always refers to the legs, never to the hypotenuse. And you can see that who is opposite and who is adjacent depends on which angle you're focusing on to. What does opposite mean? It means opposite to the angle that you're focusing on, which was theta here. And what does adjacent mean? Adjacent means adjacent to the angle that you're focusing on, which is theta in part A. All right, so then we can say that the sine of theta, well, SO stands for opposite over hypotenuse. Well, our opposite side here was V, and the hypotenuse is K. So there's sine theta. Then cosine theta, that's adjacent over hypotenuse. This is the way that we use the SOH CAH TOA memory aid. And our adjacent side, we've decided, was Q, and our hypotenuse is K. And then tangent, TOA. Tangent equals opposite over adjacent. Is this a good way to write it? Nope, that's terrible. This is meaningless. Sine, cosine, and tangent those are functions that need an input of a variable. So just saying tangent doesn't mean anything. You have to say tangent of theta. You have to say which angle you're focusing on. So if you write this, that's meaningless. You've got to write this. If you write this, that's meaningless. You've got to write this. Okay. So here we would have tangent of theta equals the opposite side, which is V, over adjacent, Q. You can see that we're focusing on theta. Oops, looks like I made that same mistake. This was not a trick for you. That was just a careless mistake. Did you catch my mistake there? That was not good. So this should be cosine theta. Okay, so let's see. I was saying that you can see we're focusing on theta because that's the angle that we're taking the sine, cosine, and tangent of. So opposite and adjacent here mean opposite or adjacent to theta. So that's how we would do part A. All right, if you had trouble with this problem, hopefully now it won't give you trouble, and now you should pause the video and try part B. So the first thing you have to do for part B is relabel the sides. Relabel the sides. In fact, maybe rewrite the triangle. So I'm going to rewrite the triangle here. Maybe I'll just use technology and copy it. Okay. And now I'm going to relabel the opposite, adjacent, and hypotenuse sides. So now, the first thing is, which angle are we focusing on for part B? For part B, which angle are we focusing on? Well, now we're focusing on alpha. So the first thing to do is to erase this asterisk and say, now we're focusing on this angle, alpha. Is this still the hypotenuse? Yeah, this is still the hypotenuse because it's still opposite the 90 degrees. But do you see that the opposite and adjacent sides have to change? Now this side, now this is the leg that is adjacent to alpha. Here's the leg that's adjacent to alpha. Why don't we call this adjacent? Isn't this adjacent to alpha? Well, yes, but this is the hypotenuse. Remember, adjacent means the leg that's adjacent. This is the leg that's adjacent. Not adjacent doesn't refer to the hypotenuse, and clearly this is the side that's opposite to alpha. Okay, so the big lesson that you need to take from this is who is opposite and who is adjacent is not set in stone. It depends on which angle you're focusing on. When we focused on theta, adjacent was on the left and opposite was on the right. But now that we're focusing on alpha, opposite's on the left and adjacent is on the right. I think that's the biggest source of mistakes, that students don't understand that opposite and adjacent depends on which angle you're focusing on. Okay, so now we can work through the sine of alpha. We'll remind ourselves of our memory aid, SOHCAH TOA. So the sine of alpha, SO, will be the opposite side over the hypotenuse. Now the opposite side is Q, and the hypotenuse is still K. And we have the cosine equals the adjacent side over the hypotenuse. Did you see I made a mistake? I made a mistake. Got to include the angle. Cosine is meaningless unless you include the angle. Cosine, now we're taking the cosine of alpha. Now the adjacent side is V, and the hypotenuse is K. And for tangent, TOA. Tangent is opposite over adjacent. So that's Q over V. So we have our answers. Now, normally you wouldn't figure out so many sines, cosines, and tangents for one individual problem. And normally you wouldn't use both one angle and the other angle on the same problem, but it's good to do that once or twice for practice just so that you get a deep understanding of how sine, cosine, and tangent work. Notice that none of these sines, cosines, or tangents, none of these were the same for the two different angles. Every sine, cosine, and tangent changes when you change the angle that you're focusing on. So I think that's a big mistake that students make. They don't pay enough attention to which angle they're focusing on. You can put in an asterisk to help you know which angle you're focusing on. All right, and again, so let's review what these terms mean. So sine is opposite over hypotenuse, cosine of the angle is adjacent over hypotenuse, tangent of the angle is opposite over adjacent. But what is the hypotenuse? The side opposite the 90 degrees. What is the opposite? It's the leg that's opposite the angle you're focusing on. And what is the adjacent? It's the leg that is adjacent to the angle that you're focusing on. All right, so I hope now we have a clearer understanding of what sine, cosine, and tangent mean and what this memory aid SOHCAH TOA means. Let me remind you that this memory aid only applies to right triangles. This is for right triangles only. We only use the idea of SOHCAHTOA for right triangles. Please pause the video and try this problem. I hope you tried that. For this problem, we can use SOHCAHTOA. By the way, when can you use SOHCAHTOA? When is there enough information to use SOHCAHTOA? In order to use SOHCAHTOA, generally you can use SOHCAHTOA when you know one side and one of the acute angles. If you know one side and one of the acute angles, you can use SOHCAHTOA. You can use SOHCAHTOA when you have a right triangle where you know one side and one of the acute angles. Remember, the acute angles are these two angles. What about if you know two sides? Remember, if you know two sides, you can just use the Pythagorean theorem. Okay, so let's try that here. So I'm going to take my time and be systematic about this. First, let's make sure we know which angle we're focusing on, this one. Now, who are the opposite, adjacent, and hypotenuse? This side is opposite the 90, so this is the hypotenuse. Now, this side is opposite to the angle that we're focusing on. This is the leg that's opposite to the angle we're focusing on, so we'll label this as opposite. And this side is adjacent. This is the leg that's adjacent to the angle we're focusing on, so I'll label that as adjacent. Also, we should make up some symbols for these so we can do algebra, so I'll call this y and this x. All right. Then should we use sine, cosine, or tangent to solve this problem? Well, tangent won't be very helpful to us because clearly we need to use the hypotenuse. That's the number that we know. We know the hypotenuse. So we need to use the hypotenuse here, and tangent doesn't use the hypotenuse. So I'll use the sine and cosine instead. So the sine of the 20 degrees will be opposite over hypotenuse. So we decided that was y over 14. So to get the y by itself, I'm going to multiply both sides by 14. To get rid of this 14 in the denominator, we multiply both sides by 14, so the 14s will cancel. So now we have to do 14 sine 20. And now I need to check something. You have to check to make sure you're in degrees mode rather than radians mode. So in this calculator, I would go to mode, and I can see I'm in degrees mode, not radians mode. So make sure you're in the right mode on your calculator. I can get out of this screen by going second quit. All right, so I'm in degrees mode. And I'll round that out to 4.79. We could build that into our sketch. Okay. And then we also have cosine 20 degrees, ca, that's the adjacent side over the hypotenuse. By the way, if you wanted to, what's the other way you could now use to find x? How else could you find x now? Now that we know two sides, you could use the Pythagorean theorem. You can do that if you want, but our goal right now is to practice SOHCAHTOA. So I want to do it the SOHCAHTOA way so I can get practice. So this will be x over our hypotenuse, which is 14. So then we need to multiply both sides by 14. So the 14s will cancel. And then here we can do 14 cosine 20. And we'll get 13.16. How can you check if those are correct? Well, for one thing, they should both be less than the hypotenuse, because remember the hypotenuse is the longest side, and that's what happened here. Now, let's discuss another useful way to check whether your answers make sense for SOHCAHTOA type problems. So here we're going to use this idea. When comparing two sides of a triangle, the longer side is opposite the bigger angle. When you're comparing sides, the longer side is opposite the bigger angle. So we can use that then to compare these two sides. So numerically, this side, about 13, came out to be bigger than this side of about 5. And we can check that by checking that the bigger side is opposite the bigger angle. And you can see that that worked, right? It should be obvious to you that this is the bigger angle up here. This is 70. And you can see that the longer side really did come out opposite the bigger angle. And the smaller side is opposite the smaller angle. So for example, if this side had come out to be, say, I don't know, 2.8, if this side had come out to be 2.8 and this was still 4.79, we would know that that was wrong. That would be wrong because we can't get a smaller number for this side. We shouldn't get a smaller number for this side than for this side, since this side is opposite the bigger angle. So this would be a wrong answer. And the answers that we got seem to make sense because this bigger side is opposite the bigger angle of 70 and this smaller side is opposite the smaller angle of 20. By the way, I did already mention this rule before when we were just explaining why the hypotenuse is always the longest side of a right triangle. And you can see how that applies here. So this angle is 70, but there's another angle that's even bigger here, which is 90. And you can see that the bigger angle of 90 is opposite the longer side of 14. And the smaller angle of 70 is opposite the smaller side of 13.16. This side is shorter than this one. And then the smallest angle of all is opposite the smallest side of all. Smallest side opposite, smallest angle opposite smallest side, middle angle opposite middle length side, and greatest angle opposite greatest side. Well, in a right triangle, the 90-degree angle is always the biggest angle, and therefore, as we already mentioned earlier, in a right triangle, the hypotenuse will always be the longest side. That's a consequence of this rule. I think that's a real useful rule to learn because it gives you a real good way to check your answers when you're doing trigonometry. So I encourage you to learn this rule and use it to check your answers when you're doing trigonometry. That might help you to catch some mistakes that you might otherwise make. Now, one more way we could check our answers is simply to look at how long the sides are drawn as. You can see that in this picture, the horizontal side was simply drawn as a much longer side than the vertical side. And you can see our numbers are consistent with that. This side looks bigger the way it's drawn, and it corresponds to the bigger number. This side looks shorter the way it's drawn, and it did correspond to the shorter number. So that, again, it confirms our results. Now, obviously, that last technique is only effective if you trust that the diagram was drawn roughly to scale. On the other hand, this technique of the idea that the longer side is opposite the bigger angle, this is a technique that will work for any triangle, even when the picture is not drawn to scale. So this is a more robust technique because this works even when the picture is not drawn to scale. Finally, there's one more way that you could have checked these answers that's more time-consuming. If you really want to check that these are correct, you could plug them into the Pythagorean theorem and make sure they satisfy the Pythagorean theorem. Does 4.79 squared plus 13.16 squared really equal 14 squared? If they do, that's a strong indication that you did the problem correctly. And if they don't, that's an indication that you made a mistake. It won't come out exact but it should, because of rounding error, but it should be pretty close. So that's something you can do if you really want to be sure that you got it right. On the other hand, that's a lot more time-consuming than the other two methods I mentioned for checking if your answers made sense. So I would emphasize the quicker methods that I mentioned. Usually you're probably not going to want to take the time to check these in the Pythagorean theorem separately, but that is an option. So there's really a whole bunch of things that you can do to check whether your answers make sense on these problems. All right. All right, so that's another example of how to use SOH CAH TOA. Remember here we didn't use tangent because the tangent doesn't use the hypotenuse. And we needed to use the hypotenuse here because the hypotenuse was the number that we knew in this triangle. Okay, now try this problem. So this is the same problem as before, but for practice, this time instead of using the 20-degree angle, I'd like to use this angle up here. So please pause the video and try to figure out all the unknown sides using this angle. Of course, that's not something you would have to do in real life. Usually you would use the angle that you're given, but this is good practice so that we really build an understanding of how sine, cosine, and tangent work. So I hope you paused the video and actually did that to build your understanding. So the first thing we're going to have to do here is, well, I guess we can say that these are still the sides that we're trying to figure out. How big is this? Well, remember the acute angles add up to 90. So this must be 70 degrees so that it'll add up with 20 to 90 degrees. And now I'm going to put the asterisk over here because now we're focusing based on this on the top angle. Again, in real life, you can focus on whichever angle you want. On real problems, you can focus on whichever angle you want, and usually you would focus on the angle that was given. But just for practice, to build our understanding, in this problem, we're going to focus on this top angle to build our understanding. All right, and now we can apply SOH CAH TOA. Who's the hypotenuse? Well, the hypotenuse is the same as before. It's the side opposite the 90 degrees. Who's adjacent? Adjacent is the leg that's adjacent to the angle we're focusing on, which is the 70 now. And opposite is the leg, which is opposite to the 70, which is this leg. And again, we can call this side x and this side y. And again, I'll use sine and cosine to solve this problem because they use the hypotenuse, which is the number we know. So now I'm going to take not the sine of 20, but now I'm going to take the sine of 70 because that's the angle we're focusing on. And we know the sine is opposite over hypotenuse. So that would be here x over 14. So now we multiply both sides by 14 to get rid of this 14. And over here, we've got the cosine of 70. Well, that will be adjacent over hypotenuse. So that cosine will be adjacent, y over 14. So we'll multiply both sides by 14 to get rid of this 14. Now we can pull over our calculator. 14 sine 70. So that will give us 13.16 for x. And 14 cosine 70. That'll give us 4.79 for y. Now, how should these answers compare to the answers from the previous problem? Well, if we did things correctly, they should be exactly the same. So let's see. 13.16 for x, yes, and 4.79 for y. Good. All right, so again, we just did that for practice. Normally, you would just use the angle that was given to you by the problem, but for practice, it's good to use the opposite angle to really get a better feel for how sine, cosine, and tangent work. Okay, so let's try a quiz question. Pause the video and decide whether this is true or false. So that statement is false. But a lot of students think it's true, or maybe they just kind of assume it's true without thinking. Why do a lot of students assume this? Well, on most problems, we do use cosine for the horizontal leg, and on most problems, we do use sine for the vertical leg. For example, that's what we did on this problem, right? We used the cosine for x, the horizontal leg, and we used sine for y, the vertical leg. So in this example, we did follow the rule in this sentence. In this example, we did follow this rule, and that's what you're going to do in the majority of problems. In the majority of problems, you will use cosine for horizontal and sine for vertical, and that fools or tricks a lot of students into thinking that that always works. So that's what's important to understand, that that doesn't always work. It only works if you're focusing on this angle. But what about if you focus on the top angle? Well, notice now that we're focusing on the top angle, now did we still use cosine for the horizontal leg? No, now we used cosine for the vertical leg, y. And now that we're focusing on this angle, we did not use sine for the vertical leg, we used sine for the horizontal leg. This is usually true on most problems, but it's not a general rule that you can rely on. You know, for some reason, students seem to make a lot of mistakes using sine, cosine, and tangent. I never really understand why they make so many mistakes, because to me it seems like a pretty easy topic. But I think it's maybe because of this issue right here. I think a lot of students get fooled into thinking that you always use cosine for horizontal and sine for vertical, since that's what usually happens, and they don't realize that it depends on which angle you're focusing on. Okay, so be careful. Remember that there are some patterns that work frequently for sine, cosine, and tangent, but that also have important exceptions. So how could we reword this so it's always true? How can we reword this so it's always true? I hope you came up with an answer. Well, we've already talked about that. What's always true is you use cosine for the adjacent leg, and you use sine for the opposite leg. That's what SOHCAH TOA tells us. Use opposite leg for sine and adjacent leg for cosine. And by adjacent, we mean adjacent to the angle that we're focusing on. And by opposite, we mean opposite to the angle that we're focusing on. So this is the only rule that always works. Like I said, even though this should be a really easy topic, students often make mistakes. And I think it's because they get to be a little bit too much on autopilot, and they assume all the problems are the same, and they don't really think in terms of adjacent and opposite. They just try to keep applying the same pattern that worked on most of the problems. So don't do that. Don't go on autopilot. Don't just apply patterns. Always think about SOHCAH TOA. Always think about which is the angle I'm focusing on, who is adjacent, and who's opposite. I'm going to say that one more time. To avoid the common mistakes, don't be on autopilot when you apply sine and cosine and tangent. Don't just follow the same pattern for every problem. Instead, always ask, which angle am I focusing on? And which side is the adjacent side, which leg is the adjacent leg, and which leg is the opposite leg. If you do that, then this should be a pretty easy topic for you, and you should avoid the common student mistakes. So one more time. It's true that we usually use cosine for the horizontal leg and sine for the vertical leg, but don't let that trick you. Even though this is usually true, there's also many important exceptions where it's not true, so don't use this as a general rule. Instead, focus on who's adjacent and who's opposite and which angle you're focusing on. That's one of the main lessons I wanted to teach by doing this same problem twice. By doing the same triangle twice, I wanted to show that the only rule that always works is to focus on, is that cosine is used for the adjacent leg and sine is used for the opposite leg. And who is adjacent and who is opposite, that's the big lesson. Who is adjacent and who is opposite depends on which angle you're focusing on. Who is adjacent, which leg is adjacent, and which leg is opposite depends on which angle you're focusing on. I think that's what students don't understand that leads them to make mistakes in this area. Now, that raises an obvious question. Which angle is the correct angle to focus on? Is it correct to focus on the 20-degree angle, or is it correct to focus on this top angle of 70 degrees? What do you think? Well, in general, they're both correct. In general, you can focus on whichever angle you please, and you should be able to see that from these two examples right here. When we focused on the 20-degree angle, we got these two answers. But you can see that when we decided to focus on the other angle, the 70 degrees, we got the same answers, right? This answer is the same as this, and this answer is the same as that. Since the answers were the same, that shows you that you can focus on whichever angle you please. Now, of course, on this particular problem, in this particular case, the second question specifically instructed you to use the angle at the top. But that was just for practice. You're rarely going to see that on other physics problems. Other physics problems usually will not instruct you which angle to focus on, and in that case, you should focus on whichever angle you please, whichever is more convenient. How do you know which one is going to be more convenient? Well, usually it's more convenient to focus on the angle that is given in the problem. For example, here we were originally given this 20 degrees. We were not given the 70 degrees. So it's more convenient to use the 20 degrees. For one thing, that way your solution is more likely to match the solution you'll see in the answer key. But on the other hand, we saw that you're not required to use this angle. If you feel like it, even if you're given the 20 degrees, you could write down the 70 and use that as the angle you're focusing on. It's just a little less convenient. Also, if you're given not a number, but a symbol, if you're given a symbol for an angle, then it's actually a lot more convenient to focus on the angle that you're given. So if you were given that this angle was theta, it's much more convenient to focus on this angle than the top angle because we weren't given a symbol for the top angle. It's still possible to solve the problem by focusing on the top angle, but your algebra would be significantly more complicated. So this would be a good example where it's much more convenient to focus on the angle for which you're given the symbol. You're just given a number, it's still probably best to focus on that number that you're given. That way your work will more closely match the answer key, and you give yourself one fewer chance to make a mistake if you don't require yourself to calculate this angle up here, simple as that calculation is. All right, so to repeat, which side is opposite and which side is adjacent depends on which of the two acute angles you choose to focus on. Technically speaking, it's perfectly okay to choose to focus on either of the two angles, but it's usually more convenient to focus on the angle that was given to you in the problem. And then just remember, once again, once you decide that angle that you're focusing on, remember that then based on that, you have to decide which side is opposite and which side is adjacent. For example, if we're focusing on the 20 degrees, the vertical side is opposite. But if we happen to focus on the 70 degrees, then the vertical side is adjacent. Please pause the video and try this problem. All right, it's always a good idea to build what the question is into your picture, so I'll do that. And we need to give names to these sides. You can call them whatever you want. So I'll call this side X, and I'll call this side Y. You can give any names that you want to those sides. Also, this is a no number problem, so it might help to list the givens. What are we given? Well, the givens are the symbols that were mentioned in the problem, and that includes the symbols that were indicated in the picture. So is this a given? Yes, it was given in the problem, in the picture. Is this a given? Yes. Is this a given? No, this is a symbol we made up. Is this a given? No, this is a symbol we made up. So these are the givens for the problem, the symbols that were originally in the diagram. So our final answer should include only these two symbols. Those are the rules of the game for a no number problem in physics. Our final answer should include only these two symbols. Okay. And this is a case where we can use SOHCAHTOA. Remember when you can use SOHCAHTOA? Did we talk about that? You can use SOHCAHTOA when you know one side and one of the acute angles in a right triangle. One side and one acute angle. Well, here we know this side and this acute angle. And if you're given the symbol, we treat it as if we know it. So we can do SOHCAHTOA here. Now again, we're not going to use tangent because we want to use the symbol that we were given for this side. Well, let's label which is us opposite and adjacent hypotenuse. This is the hypotenuse. because it's opposite to the 90-degree angle. This is the hypotenuse because it's opposite to the 90-degree angle. Remember, hypotenuse does not have to be the diagonal side. You're probably used to seeing a hypotenuse that's a diagonal side, but don't be on autopilot. The hypotenuse could be a vertical or a horizontal side. It's just the side that's opposite the 90-degree angle. And then which angle are we going to focus on? Well, we could focus on this one, but it's much more convenient to focus on the bottom angle because that's where we were given the symbol. So I'm going to put in the asterisk to show I'm focusing on this angle where we were given the symbol. Then this leg is adjacent to that angle that we're focusing on, and this leg is opposite to that angle that we're focusing on. So again, we don't want to use tangent because that would not let us use the hypotenuse, which is what we know about here. So we can say here that the sine of theta is equal to opposite over hypotenuse. So the sine of theta here would be x over d. Now what? Well, remember we're trying to solve for x. We're trying to solve for x, so we need to multiply both sides by d to get the x by itself. This is where, on a no number problem, it's easy to get confused about who you're solving for. So it's important to use a question mark to indicate which symbol we're solving for and which are the givens. So the d's here cancel, and we end up with x equals d sine theta. Okay, and now we have to do it all over again for cosine. Cosine equals adjacent over hypotenuse. So cosine equals adjacent, which is y, over hypotenuse, which is d. Is this a good equation? No, this is terrible because I forgot the angle. The angle is theta. So remember that you have to include the angle. All right, and now again we have to multiply both sides by d because we're trying to solve for y. We need to get the y by itself. If you needed to use this to, in another part of the problem, you might want to build this information now into your sketch. Okay, so now we've solved the problem. So this gives us some practice with applying SOHCAHTOA to a no number problem, which is something that you're very likely to have to do in your physics class. Remember I said that your final answer should only include d and theta, and you can see this answer includes only d and theta, and this answer includes only d and theta. So for example, you would not want to include x or y in your answer. Of course, you can put the x over here to show that's what you solved for, but there can't be any x or y over here. And you can put the y here to show that this is what you're solving for, but there shouldn't be any x or y over here. These symbols should only be the givens. Those are the rules of the game for a no number problem. Okay, now I'm purposely trying to give you kind of weird looking right triangles to make sure that you're not on autopilot. So again, a lot of students assume that you use sine and cosine to find the horizontal leg and the vertical leg. But notice that in this case, we weren't trying to find the horizontal or the vertical leg. We were trying to find two diagonal legs. The only thing that always works is that the hypotenuse is opposite the 90-degree angle, and that you need to know which angle you're focusing on, and then the sine is used to find the opposite leg, and the cosine is used to find the adjacent leg. So don't be on autopilot, just use those general principles for each new problem, and then you should be able to deal with whatever is thrown at you in the problems. You might have noticed here that I've been writing down all of my steps. I always put an asterisk for which angle I'm focusing on, and I always label all the sides, hypotenuse, opposite, and adjacent, and I write down every single step here in the algebra. Now, you'll probably eventually get to the point where you think these problems are easy, and then you don't have to write down all these steps, and that's fine. That's great. But until the problems are easy, you should write down the steps. So if right now you sometimes make mistakes on these problems or you get confused, then you should imitate what I'm doing and write down all the steps. You shouldn't start skipping any of these steps until you're getting 100% of these problems right in all situations. Until then, it's good to write down each of these steps so that you really understand the logic of what you're doing and you make sure that you're not on autopilot. Remember, the reason you don't want to be on autopilot is because then the professor can trick you by giving you a problem where the autopilot doesn't work. If the professor gives you a problem that's a little bit different than the ones that you've seen before, and you're just applying patterns mechanically rather than applying the general principles, you can easily make a mistake. You want to get to the point where these problems are boringly easy, because this is not supposed to be the hard part of physics. If you're finding this already to be a boring video, that's great. This is supposed to be a boring video. This is supposed to be boringly easy material. So keep practicing this and keep writing down all the steps till you get to the point where this is boringly easy. Not boringly easy for you yet. That means that you need to keep practicing it until you get to that point. Try this problem. Okay, now this problem might look a little bit different than some of the ones we've done so far, but we do know one side and one of the acute angles. And we've learned that when you know a side and an acute angle, you can use SOH CAH TOA to find the remaining sides. When you know one side and one acute angle of a right triangle, that's when you can use SOH CAH TOA to find the lengths of both of the remaining sides. So even though this problem might look a little different than we're used to, we should be able to use SOH CAH TOA here. So I suppose that we need to, well, the first thing to do is to build the question into the sketch. The question is asking us for this length and this length. It's always good to use a symbol for what the question is asking you when appropriate. So why don't we call this length? We can choose any symbol we want here. I'm going to choose X to stand for this length. And I'll choose R. Again, I can choose any symbol I like, but I'm going to choose R to stand for this length. So notice it helps to make up some symbols sometimes to stand for the lengths so that we can do algebra on the problem. Then we want to label the opposite, adjacent, and hypotenuse. Well, this side, R, is the hypotenuse because it's across from the 90-degree angle. To find opposite and adjacent, we need to decide which angle we're focusing on. Well, we were given the 60-degree angle, so it's natural to focus on the 60-degree angle. I'll put in the asterisk to remind myself that I'm focusing on the 60-degree angle. And then this side X is adjacent to the 60-degree angle, and this side 12 is opposite to the 60-degree angle. Now we can use SOH CAH TOA to set up some equations. Now, who should we use? Sine, cosine, or tangent? Well, notice that the one number that we know here is for the opposite side. We know the number for the opposite side, so we need to use equations right now that involve the opposite side. So sine would be a good function to use because that would let us use the opposite side with the number 12. And tangent would also be a good function to use now because that would let us use the opposite side with the number 12. Cosine would not be a good function to use yet. It would not be a good idea to use cosine because cosine would not allow us to use this number on the opposite side. The cosine doesn't deal with the opposite side. So now we could use either the sine or the tangent to continue with solving the problem. You can choose whichever you like. I think I'll go ahead and use the sine. So the equation that I get from that is that the sine of the angle equals, I'll just go ahead and say it's the 60-degree angle. The sine of the 60-degree angle equals the length of the opposite side over the hypotenuse. Sine is opposite over hypotenuse. And we've decided the opposite side has length 12. And the hypotenuse we don't know, but we made up the symbol R for that. You can see why it was useful to make up a symbol. We need a symbol in order to use algebra to solve for that unknown. Okay, now this equation looks a little bit different than the equations we've gotten previously in this video, so we might have to use slightly different algebra in order to solve it. Do you know how to solve this equation? Well, we want to get the r by itself. And the first step for getting the r by itself is to get the r out of the denominator. We have to get the r out of the bottom of this fraction. Well, the way to get rid of a denominator is to multiply by that value. So I'm going to multiply both sides of the equation by r. That has the advantage of canceling these r's. And you can see I accomplished what I wanted. I got the r by itself. Now we want to continue to get the r. Oh, I misspoke, didn't I? What I meant to say is that I didn't get the r by itself yet. I meant to say that I got the r out of the denominator. We accomplished what we wanted with this step. We got the r out of the denominator, but we have not gotten the r by itself yet. Now we need to get the r away from the sine 60 term. Well, you probably know how to do that. We need to divide both sides by sine 60. Now the r is isolated and we're ready to use our calculator. 12 divided by sine of 60 degrees. Because this digit is a 5, I'll round up this digit. So this rounds to 13.9. 13.9. So it's always a good idea when you figure something out to go back and build that new information into your sketch. So I'll take that 13.9 and I'll build that into the sketch. You should always check to see if your results make sense. Well, this does make sense because it's bigger than 12. Remember, the hypotenuse has to be longer than the legs, so it makes sense that this came out bigger than 12. If this answer had come out to be, say, 9, if this had come out to be 9, we would have known we made a mistake, right? If this came out to be 9, we would know we'd made a mistake because the hypotenuse can't be shorter than the leg. So you should always be able to kind of check whether you're on the right track with these types of problems by comparing the lengths of the various sides. For example, we know that the hypotenuse should be longer than the legs, and that gives you a way to check whether you're doing things correctly. You might not think of that, though, unless you try to build what you figured out back into your sketch. So that's always a good idea. Okay. So notice here that we had to use a little algebra that we haven't had to use in the past. So I hope you followed this, the algebra here. And if the algebra here gave you difficulty, you should mark this problem and try it again later to make sure that you remember how we used algebra here to get the r out of the denominator of the fraction. That's an algebra that you might need to use when you're applying SOH CAH TOA. Now we're not done because the problem also asked us to find x. Now, can you see that at this point, we have two options. We could use either cosine or tangent because we know both of these sides. Because we know both of these two sides, we could use either cosine or tangent now to find this side. You can make whichever choice you feel like. I think I'll go ahead and use cosine. You could use tangent. But I'm going to use cosine now. So we have that the cosine of 60 degrees equals adjacent over hypotenuse, CAH. The adjacent side we've labeled as x. Again, notice that we wouldn't be able to solve the problem if we hadn't come up with symbols for these unknown sides. We just made the symbols up, but they were very useful to us now in solving the problem. Sometimes you have to make up a symbol in order to be able to do algebra. And the hypotenuse is the number we just figured out, 13.9. So we'll use the number we just figured out, 13.9 here. And now I think we've already seen many times how to solve this simple equation, this type of simple equation. To get the x by itself, I'll multiply both sides by 13.9. Now we're ready to use our calculator. 13.9 cosine 60. I'll just leave that as 6.95. And again, it would be a good idea to build this result back into our sketch. Here's our 6.95 result. Okay, so now we're about done. We have our two answers, 13.9 and 6.95, but we should stop and ask ourselves, let's see, did we answer the right question? Did we answer the entire question? Well, yes, the question asked us for these two lengths, and we figured it out. Does this answer make sense? Well, we can decide if this makes sense by comparing it to our two other numbers that we know. First of all, notice that this number is smaller than 13.9, and that makes sense because the leg should be shorter than the hypotenuse. If we had gotten that x was 15, we would know that that was wrong because the leg should not be longer than the hypotenuse. This we would know is wrong. This answer makes sense. But we can also compare this leg to the 12. Remember this idea that we talked about earlier. Well, I think it should be clear that this is the bigger of the acute angles. And this angle up here is the smaller of the acute angles. And notice that we do have that the bigger angle is opposite the bigger side, the longer side, and the smaller angle is opposite the smaller side. So that checks out, and that's a confirmation that we did this correctly. If this number had come out to be, say, 12.5, we would know 12.5 has to be wrong for this side. It's not possible that this side could be longer than this one because it's opposite the smaller angle, not the bigger angle. I think it's really good to get into the habit of learning this idea and using it to check your results when you do trigonometry. This is a very easy check, and it can help you to really catch a bunch of mistakes, including mistakes you might make on exams. When you're comparing the sides, the longer side should be opposite the bigger angle, and if it's not, that indicates that you made a mistake. Another way we could check our answers is simply to look at the picture. You can see that this side is drawn as being longer than this one. So that would seem to predict that this number should be bigger than this number. Now, of course, that only makes sense if you trust that the diagram is drawn to scale. What I mean is that you can only trust the drawn lengths if this angle is roughly to scale. If you think this angle is roughly to scale, then you can trust that the side that's drawn longer is the side that should also be numerically longer. But even if the angle was not to scale, this is an idea that always works. Okay, so there are some quick checks that you can do that can give you a pretty reliable way of checking whether you did a SOHCAHTOA type problem correctly, and I encourage you to get into the habit of making those checks. Remember, longer side opposite the bigger angle. And by the way, remember again that there's usually more than one correct way to solve a SOHCAHTOA type problem. In this case, we chose to start by using sine of 60, and then we chose to follow that up by using cosine of 60. But that's not the only possible way you can solve the problem. You could also have solved the problem by using the tangent of 60. If you want an exercise or more practice, you can try to duplicate some of these results using tangent. So this is a good solution, but it's not the only way to solve the problem. Another thing we could have done at this point, something else we could have done is instead of using SOHCAHTOA, here we could use the Pythagorean theorem. Remember, once you know two sides, you can use the Pythagorean theorem to find the third side. So we could have used the Pythagorean theorem also as part of our solution. So there's more than one way to solve a SOHCAHTOA type problem. All right, well, did you get this problem correct? If you didn't get it correct, that might be because you did the problem kind of on autopilot, and you were just kind of repeating a pattern from previous problems without applying general principles. So the tricky part of this problem is that in this case we divided by the sine. Here we had to divide by the sine. Whereas I think in the previous problems we were usually multiplying by the sine or cosine. Our previous problems, I think, generally looked like this, where we ended up multiplying a number by the sine or multiplying a number by the cosine, rather than dividing by the sine as we had to do here. So if you were on autopilot, so to speak, you might have mechanically tried to multiply 12 by the sine, and then you would have gotten an incorrect answer. So how can you avoid that? What's the correct way to do the problem? Well, the correct way is, rather than just repeating patterns, to always use the general principles. So I'll just review one more time what the general principles are. The general principles are to label, or at least mentally identify, the hypotenuse, opposite side, and adjacent side. Then we use the SOHCAHTOA memory aid to set up an algebraic equation. And then notice that as we solve the algebraic equation, the algebra tells us automatically whether we should be multiplying by the sine or dividing by the sine. We didn't have to predict whether we were going to divide or multiply by sine of 60. We just set up the equation correctly based on SOHCAHTOA, and then when we worked through the algebra carefully, the algebraic solution simply told us that we had to divide by the sine. And that's the right way to do these problems. Don't do them on autopilot. Don't assume that every problem follows the same pattern. Instead, identify the various sides and then set up the correct algebraic equation and let the algebra show you what calculations you need to do. I think that these problems are actually not very difficult. I think they're pretty easy, so why do so many students have trouble with them? Well, again, it might be because students are trying to do the problems on autopilot without actually setting up the algebra correctly and then working through the algebraic solution. Now, I can see that that's tempting because in most questions, on most problems, solving on autopilot actually works for SOHCAHTOA. Most problems, you do multiply the number by the sine or the cosine. Problems are like this one, where you do end up multiplying the given number by the sine or cosine. So I can see why it can be tempting to think that autopilot is fine and that you can do all these problems the same way. But if you want to get all the problems right, that's not going to work, because even though most of the problems will probably fit into this pattern, there will also be a significant fraction that do not fall into the pattern. There will be a significant fraction that look like this, or maybe that look like some other unusual pattern where doing the problems on autopilot, so to speak, will give you the wrong answer. And when are you especially likely to see those unusual problems? You're especially likely to see those unusual problems on your exams. Professors on the exam want to make sure that you actually understand the SOHCAHTOA trigonometry and that you're not just working on autopilot. So on the exam is where the professor is especially likely to give you unusual problems where you're going to get the wrong answer unless you just carefully set up the algebra. So don't be lulled by your homework questions into thinking that all SOHCAHTOA problems are the same. Maybe a lot of them can be solved using a general pattern, but there's a good chance you'll see some unusual problems on your exams that won't work that way. So instead, don't try to solve the problems quickly. Be sure that you're actually setting up the algebraic equation and solving it. Now, eventually, maybe you'll get to the point where you understand this material so well that you don't really have to write down all the steps for the algebraic solution. Eventually, you'll get to the point where you can recognize problems that fit into the usual pattern and problems that don't. But my experience is that early on, most students are not at that point yet. So if you're still at the point where you miss problems, then don't skip steps. And you can, this problem right here is a good test. If you got this problem incorrect when you tried it the first time, then you're not ready to start skipping steps, and you should be still writing down, setting up the algebraic equation at the beginning to avoid missing these types of problems. Try this problem. Well, this was kind of a trick question. We cannot apply SOHCAHTOA here because we don't know that this is a right triangle. It doesn't look like a right triangle, and we're not told it's a right triangle. So remember, our normal SOHCAHTOA approach only works for right triangles. So the answer here is that there's not enough information to answer. All right, so the lesson of this question is that we only apply SOH CAH TOA to right triangles, triangles where we know that there is a 90-degree angle. Please try this problem. Well, we know that this is a right triangle, so we can find the hypotenuse, which is opposite to the 90-degree angle. So this side is the hypotenuse, opposite to the 90-degree angle. Now, next, we have to determine which side we should label as opposite and which side we should label as adjacent. And the answer is, it depends. It depends on which angle we choose to focus on. That's the purpose of this problem. This problem is just designed to remind you that which leg is opposite and which leg is adjacent depends on which angle you choose to focus on. So remember, it's good to put an asterisk on the angle that you're focusing on if there's any doubt. If we choose to focus on theta, well then A is adjacent and D is opposite. But if we wanted to, we could make the alternative choice. If we wanted to, we could choose to focus on angle alpha. And in that case, D would be labeled as adjacent, and A would be labeled as opposite. Okay, so the purpose of this problem is just to remind you that which side is opposite and which side is adjacent simply depends on which angle you choose to focus on. So what's the correct choice? Which angle should you choose to focus on? And the answer is, it really doesn't matter very much. You can make whichever choice seems most convenient for the problem that you're working on. Generally, either angle will work. Usually, though, one of the angles is more convenient or easier to work with than the other. Usually, if one of the angles is already given to you, then the convention is to choose that angle. For example, do you remember this problem? In this problem, the problem gave us the 20-degree angle. So the conventional approach would be to choose to focus on this angle. It would be perfectly okay to focus on the 70-degree angle. You could solve the problem perfectly well if you focused on the 70-degree angle. And in fact, I think we did that solution. But when you're solving a normal test problem, your answer will match the solutions document usually more closely if you choose to focus on the angle that's given by the problem. Which angle should we choose to focus on here? Well, again, technically we could choose either this angle or this angle. However, in this case, our work will probably be quite a bit simpler if we choose to focus on this angle, theta, the angle that was actually given to us. At least we were given a symbol for that. You could solve the problem using this angle, but the conventional approach and the simpler approach is to choose to focus on the angle that you're given, and even if you're just given a symbol for the angle. On the other hand, in this case, in this particular problem, it happens that we were given symbols for both angles. Since we were given symbols for both angles here, you could really choose whichever angle you felt like to focus on, and you'd be able to solve the problem just fine with either choice. Okay, so again, the purpose of this problem was to remind you that which side gets labeled as opposite and which side gets labeled as adjacent depends. It depends on which of the acute angles you choose to focus on. Okay, so to review, when can you use the Pythagorean theorem? When is the Pythagorean theorem helpful? As usual, I hope that you're pausing the video and coming up with an answer each time I ask a question. When is the Pythagorean theorem helpful? Well, obviously you need a right triangle, but that's not all. You need a right triangle where you know the lengths of two of the sides. That's when you can use the Pythagorean theorem. If you know two sides of a right triangle, you can always find the third side. If you know two sides, you can always find the third side using the Pythagorean theorem. I guess this was an example right here. Here we knew these two sides, so we were able to use the Pythagorean theorem to find this side. But here's another example where we knew two sides and we could use the Pythagorean theorem to find the remaining side. So notice it doesn't matter whether we know the hypotenuse or the legs. It doesn't matter whether you know the hypotenuse or the legs. If you know any two sides, hypotenuse or legs, you can figure out the third side, whether that's a hypotenuse or a leg. How about SOHCAHTOA? Pause the video and ask yourself, when can you use SOHCAHTOA? Well, I think we already talked about that. First of all, again, it has to be a right triangle, at least based on the methods we've learned so far. And you can use SOHCAHTOA if you know one side and one of the acute angles. Obviously, in every right triangle, you know the 90-degree angle. In every right triangle, you know the 90-degree angle, or you wouldn't know it's a right triangle. But you need to also know one of the acute angles. I guess, of course, if you know one acute angle, you know all the angles. So basically, you can use SOHCAHTOA if you know the angles and one side. If you know the angles and one side, you can use SOHCAHTOA to find the lengths of the remaining two sides. So what you need is one acute angle and one side to use SOHCAHTOA. So that's a pretty powerful technique. For example, in this case, we knew just this one side and this angle. And as a result, we were able to find the other two sides. Case where we knew an angle and a side, and we were able to find the other two sides. Of course, like I said, if we know this angle, we really know this one too. And we've seen we can use either of the two angles to find the missing sides. Okay, so keep in mind that you don't need to know very much about a right triangle to be able to figure out the remaining information. You don't need to know very much about a right triangle to be able to figure out the remaining information. But there are still more, even more useful techniques. For example, we know here that when you know two sides, you can find the length of the remaining side. But what about the angles? If you know these two sides, can you also find the angles? Of course, you always know one angle. You always know the 90-degree angle. But are knowing two sides enough to figure out the acute angles? You might want to pause the video and ask yourself, what do you think? If you know two sides, is that enough to figure out one of the angles? Well, we haven't covered that technique yet, but yes. Yes, if you know two sides, you can find not just the remaining side, but also the remaining angles. And that's what we're going to cover in the next video in this series. That's also another important technique that you'll need in your physics course. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.